we are solving question 36 of GATE 2013 chemical engineering paper. The question is, in a double pipe counter current heat exchanger, the temperature profiles shown in the figure were observed. During operation, due to fouling inside the pipe, the heat transfer rate reduces to half of the original value. Assuming the flow rates and the physical properties of the fluid do not change, the LMTD in degrees Celsius in the new situation is dash. So let's look at the solution. So here we have been given a temperature profile corresponding to a counter current heat exchanger. So let's consider this as a double pipe heat exchanger. So tube side flow will enter in this direction, leave from this direction, and since we have been given the counter current flow, the shell side fluid will enter from this direction and exit from this direction. Now, and we have been given the temperature profile corresponding to that. So let's say the hot fluid is entering from 100 degrees Celsius and it leaves 60 degrees Celsius. The cold fluid will enter at 40 degrees Celsius and leave at 80 degrees Celsius. Now we have been given that during the operation, due to fouling inside the pipe, the heat transfer rate reduces to half of the original value. So let's say for case 1, heat transfer rate was Q1, and for case 2, heat transfer rate we have been given, it reduces by half, that is Q1 by 2 that we have been given. So assuming the flow rates and the physical properties of the fluids do not change, the LMTD in the given situation is this. So for this case, we have to find the LMTD. Now let's consider this case 1. So the heat balance across this heat exchanger, we can write it as Q of total Q will be equal to Q of H is equal to Q of C, where Q of H is, let's just call this as the tube side fluid as 1 and the shell side fluid as second fluid. So it will be M1 Cp1 upon delta T, and delta T in this case will be 100 minus 60, and cold fluid we are denoting it by 2, so it will become M2 Cp2 upon 100. No, so for cold fluid we are having it as 80 minus 40, so that is 80 minus 40. So this difference is also 40, this difference over here is also 40, so we will be having M1 Cp1 is equal to M2 Cp2. So this correlation we are having. Now we will be doing it for the case 2, that is the fouling case. So for this case, let's consider the outlet temperature, that is the hot fluid outlet temperature, to be T dash out. And similarly, the cold fluid outlet temperature to be, so this was T1 and this will be T2 dash out. The inlet temperature of both this fluid will remain same. Okay, so this is cold fluid outlet, and over here we will be having the hot fluid outlet, that is T1 dash out. Now for case 2, similarly we can write Q is equal to M1 Cp1 upon 100 minus of T dash out. So this was the hot fluid, so it is T1. Similarly we will be having M2 Cp2 upon, for the cold fluid it is T2 dash out minus of 40. So from the earlier case we are having this M1 Cp1 is equal to M2 Cp2. So from this, from this we can get the relation between T1 out and T2 out. So it will become 100 plus 40 is equal to T1 dash out plus T2 dash out is equal to 140. Now we have to find a value of either this T1 out or T2 out. So we will find the value of T1 out. So from the earlier slide we were having we can calculate the value of Q. So Q will become mCp delta T, and for the second case, that is the fouling case, we are having Q2 is equal to Q1 upon 2. So using this correlation we can write it as, for Q2 it will become M2 CP2 upon T2 dash 2 out minus of 40 is equal to M1 CP1 into delta T in both of these cases was 40. So that is M1 CP1, this will get cancelled out and we will be getting over here, so that is T1 dash out is equal to 40 plus 40, that will be 80 degrees Celsius. And similarly from this correlation we will be getting T2 dash out as 60 degrees Celsius. So for the hot fluid the temperature will be 80 and for the cold fluid it will be 60. So if I have to draw this temperature profile for this new set, I can draw it as the inlet will remain at 100 degrees Celsius and the outlet temperature for this hot fluid is 80 degrees Celsius from over here. Similarly the cold fluid inlet will remain same at 40 and outlet temperature is 60 degrees Celsius. So in this case the delta T at, let's say, the hot fluid at this direct at x equal to 0 will be delta T is equal to 40 degrees Celsius, and over here also delta T will be 40 degrees Celsius. So since the temperature difference at both the inlet and the outlet are 40 degrees Celsius, the log mean temperature difference will be equal to delta T, that is LMTD. We will write it as 40 degrees Celsius. So yes, since both of this delta T were same, we didn't use that formula. It will be simply this temperature difference either at inlet or exit. So that is equal to 40 degrees Celsius. So the final answer is 40 degrees Celsius.